Good evening, everyone. My name is Terry Gronwall, and I'm chairman of the Honeoye Lake Watershed Task Force. And I'd like to welcome you to our information meeting tonight about our aeration engineering planning project. We have three members of the consultant team with us tonight. We have Dr. Steve Souza, who will be leading on the presentation in a couple minutes. Scott Churn from Princeton Hydro. Steve Souza is from Clean Water Consulting, and Paul Ganser, who is a expert on aeration across the country. So these are three key team members. So again, I want to welcome you on behalf of the Honeoye Lake Watershed Task Force and the Ontario County Planning Department. We have partnered on this project, and Dr. Souza is going to get into it in a lot more detail, but I do want to go back in time just briefly. In 2018, Governor Cuomo selected Honeoye Lake for one of the lakes for a HABS action plan, and an aeration system was one of the highest priority recommendations from that study from Governor Cuomo's effort. And in 2019, the DEC completed a total maximum daily load analysis for Honeoye Lake, and also it was the highest priority recommendation, and Steve is going to get into why it is. So with that, I'm going to turn it over to Dr. Steve Souza. Steve, why don't you take it away?
All right. Well, thank you, Terry. Yes, and so this evening we're going to give you pretty much an overview of the past year and a half worth of work that we've been conducting on the Honeoye Lake Aeration System Engineering Planning Project. And I want to begin by first extending my thanks to our project sponsors, that being Ontario County Planning Department, led by Betsy Landry, and then the Honeoye Lake Watershed Task Force, led by Terry Gronwall. And really, both Betsy and Terry have been really deeply involved in this project from day one, and helped keep things moving along with all the COVID challenges, and also very instrumental in making sure that the final report speaks well to the subject and is in a format that is understandable by everyone. The project team, as Terry pointed out, Princeton Hydro is the prime. I am a subcontractor to Princeton Hydro. I served as a principal investigator. Some of you may know me as the founder and past president of Princeton Hydro, but I retired from the company in 2018, but still stay involved with them on some projects. Scott Churn from Princeton Hydro served as a project manager. Scott has about 20 years of experience in limnological projects, and has probably overseen close to 100 aeration installation projects throughout the Northeast and Mid-Atlantic states. Jeffrey Gall is the president of Princeton Hydro. He served as the engineer on record. Dr. Paul Ganser, foremost authority on oxygenation systems, well respected and highly publicized. Again, a national expert on not only aeration, but especially on oxygenation. And then Patrick Goodwin, certified lake manager with Vertex Aquatic Solutions, also highly experienced with aeration systems. And Patrick also worked with us in the earliest study that was conducted by Princeton Hydro for DEC. The project team also consisted of a local project committee, and I have to extend my deep thanks to all those folks. Dave Baker, board member of the town of Richmond. Without doubt, Dr. Bruce Gilman and Dr. Nelson Harrison, both of whom really dedicated their careers to the study of Honeoye Lake. And I've had the pleasure of working with Bruce since the early 2000s, and both were a wealth of knowledge and really helped us out tremendously in this study. And Linda Vanderbeck, board member of Honeoye Valley Association, it's very astute insight and provided a lot of assistance also in the development of the final report. I'd be remiss if I didn't spend just a little bit of time talking about the funding for this project, which was provided through the Environmental Protection Fund, administered by the New York State Department of Environmental Conservation. And then additional funding was also provided by the Honeoye Lake Watershed Task Force and Ontario County Water Resources Council. So thanks to those funding sources. Okay, so we're going to jump into things, and I am going to cover a fair amount tonight, relatively quick. This will sort of be a little bit of Limnology 101, but directed specifically to Honeoye Lake. And a lot of you probably have heard much of this, but it begs repeating. So first off, we have all come to know that phosphorus is the primary driver of harmful algae blooms, and definitely is the primary driver of Honeoye Lake's harmful algae blooms. And what that really amounts to is that we recognize that the more phosphorus that's present in the lake makes the lake more prone to experience a harmful algae bloom. So the recommendation that has come out of numerous studies, including some work that I did back in the early 2000s, is that we need to put Honeoye Lake on a phosphorus diet. That was no surprise. Because if we reduce the amount of food, that being the amount of phosphorus that's entering the lake, we can reduce the chance of experiencing algae blooms, and that includes cyanobacteria-driven harmful algae blooms. So the goal of this project, and the goal of really the overall management of Honeoye Lake, focuses on a reduction in phosphorus loading. Now, phosphorus loading comes from a lot of sources. So in order for us to put the lake on a diet, we need to start with identifying where all this phosphorus is coming from and then quantifying it, how much is coming from various sources. And then once we have those two pieces of information in place, then we can start to prioritize where our management efforts need to take us. And multiple studies conducted by multiple researchers, including Dr. Gilman and Dr. Harrison, really point to the fact that there's an internal source of phosphorus that emanates from the sediments of the lake under anoxic conditions, meaning when there's no oxygen present, that is the primary driver of these HABs that we've been experiencing. And therefore, that's where our attention needs to be placed. So why prioritize the source of phosphorus? Well, number one, as you'll see, the amount. There is a large amount of phosphorus that's associated with this internal source. Secondly, the timing, which is extremely important. The majority of that internal source emanates during the summer months when we're most likely to experience a HAB because we have warm water conditions, plenty of sunlight. Thirdly, the type of phosphorus that's released from the sediments during these periods when there's no oxygen at the bottom of the lake is highly bioavailable, meaning that it is readily assimilated and utilized by algae. So it can quickly lead to the development of a lot of algal cells and resulting in a major bloom. So that's the bad news. But the good news is we know, based on work that's been conducted nationwide since the 1980s, that this internal load is relatively, I wouldn't say easy so much, but it is somewhat relatively easy to control. And more importantly, we can successfully control that load, more so than we can septic loading, more so than we can control stormwater loading. So that's the good news. We have a load that is large, comes at the wrong time of year, definitely very bioavailable, but can be successfully controlled. So we're going to examine all of that, for the balance of this presentation. So let's look a little bit closer at what this internal load means. Where's it coming from? Well, every day, every month, every year, phosphorus accumulates in the lake sediments. This happens with every single lake. So phosphorus washes in with stormwater runoff. It comes in with sediment, leaf litter, etc. Fish die, plants die. That phosphorus accumulates in the sediment of the lake. Now, the majority of the bioavailable phosphorus, the phosphates, are bound to iron. And that's a good thing. So as long as they can remain chemically bonded to iron, they're not immediately available for uptake and utilization by algae or cyanobacteria. However, what ends up happening is that when there's no oxygen present at the bottom of the lake, or over any sediment, regardless of whether it's at the bottom or close to the edges of the lake, there's no oxygen. That phosphorus iron bond breaks down very, very rapidly, and that releases phosphorus very rapidly at a rate that's about 3 to 5 times the normal rate into the water column. Now, if that released phosphorus circulates up close to the surface of the lake, where there's enough light to support photosynthesis, that internal load in turn causes a harmful algae bloom. So that is what's happening in Honeoye. We have we have a lake bottom that has a lot of stored phosphorus. We end up with no oxygen at the bottom of the lake at times, and that results in the rapid release of all that phosphorus in the water column. Now, as I mentioned, most of Honeoye's internal phosphorus load occurs in the middle to the latter part of the summer, and again, for reasons of longer days, warmer water, better light conditions, that all is ideal in terms of stimulating a harmful algae bloom. The amount of phosphorus that's released, remember I told you there's a lot of phosphorus that's released. It can be as much as 90% of the lake's total annual phosphorus load. That's the phosphorus load coming from every source, stormwater, atmospheric, septic, every source. It can be as much as 90% at times of the lake's total annual phosphorus load, and that amounts to about 7,000 kilograms per year, or roughly about 15,000 pounds. And these are studies that have been conducted by a number of researchers, again, Dr. Gilman, myself, others, but synthesized in 2 recent reports, the Princeton Hydro report, which was published in 2020 after DEC review, and then DEC 2 reports that I'll touch on a little bit later, a 2018 report and a 2019 report. Now, the significance of that is about a pound of phosphorus, a half a kilogram, can support over 1,000 pounds of algae. So you can see it doesn't take too much phosphorus to start to create problems. And because, as I mentioned before, the majority of the phosphorus that's released from the sediment is immediately bioavailable, it can easily be assimilated by cyanobacteria and then lead to these algae bloom problems. So this is why we need to control the lake's internal phosphorus load. We need to keep that phosphorus sequestered in the sediment. And if we can do that, then we can decrease the amount of phosphorus that's present in the lake, especially in the middle of the summer. That then lessens the opportunity for a HAB. And I'm going to stress lessens. There's a lot of other sources of phosphorus that enters the lake. As I mentioned just previously, it doesn't take much phosphorus to stimulate a bloom, but this will definitely, by controlling that internal load, it'll definitely significantly lessen the opportunity for a HAB. So for Honeoye Lake, a number of studies again have come to the conclusion and the recommendation that to keep this phosphorus sequestered in the sediment, we can do this in 2 different ways. Treat the sediment with some type of nutrient inactivant, specifically alum, and that is extremely effective, but it may be somewhat of a short-term solution. When I say short-term solution, 5 to 7 years, and then we'll need to add more alum. Or we can use some type of aeration technique to maintain oxic, which means as positive dissolved oxygen levels at the bottom of the lake. That'll keep the phosphorus bound to iron and sequester in the sediment. Again, extremely effective, and that's more of a long-term solution because we can maintain, as long as we're maintaining those oxic conditions at the bottom of the lake, that phosphorus is going to remain largely bound to iron and largely unavailable for biological use by algae and cyanobacteria. So aeration has been a long-use tool for HABs management. And those of you that have read other reports on Honeoye, you know that has been the recommendation. Look for ways to aerate the lake. Now, there are multiple ways to do that. Some techniques, as I'll show, I'll get into more detail, are designed to really mix the water column, prevent what's termed thermal stratification. We'll talk about that in a little bit. There's other techniques that don't do away totally with thermal stratification, but yet vertically mix the water column somewhat and help maintain oxygen levels at the bottom. And then the other way to do this is actually to increase oxygen down at the bottom of the lake by injecting oxygen either at the bottom or at specific layers in the lake. Overall, these techniques definitely have been demonstrated. Multiple published papers going all the way back to the 1980s showing that aeration is very effective in controlling that internal recycling. Our project goals was to build on some of the past studies, but develop a relatively detailed engineering design of the most effective system for Honeoye Lake, with our goal being, again, primarily to control and reduce the lake's internal phosphorus load. And that goal, or that, that specific goal is consistent with DEC's harmful algal management action plan, as well as the findings of the 2019 total maximum daily load report. So DEC, so the same mindset that we need to reduce the internal phosphorus load, and aeration is one of the primary ways of doing so. And then with that, again, if we can do point A and point B, then we can limit that occurrence and severity as well as duration of harmful algae blooms. So before we can talk about aerating the lake and what we're going to do and why we're going to do it, we need to talk a little bit about water itself, and specifically the thermal and density properties of water. So as water temperatures start to climb above 38 degrees Fahrenheit, the density of water starts to decrease. So warmer water is less dense than cooler water. And that leads over the summer to distinct depth zones of warmer but less dense water close to the surface of the lake, essentially like sitting over cooler, denser water that's closer to the bottom of the lake, almost like oil sitting over water. Those distinct zones of water of different densities prevents the free mixing of the water column. So now the water column can't mix from surface to bottom freely. The other thing to keep in mind that's a relationship of the water temperature and density is that warmer water holds less dissolved oxygen, meaning that it reaches a saturated stage at there's less oxygen, so it becomes saturated at lower dissolved oxygen levels. So warmer water essentially holds less dissolved oxygen than colder water. But those density and thermal property differences leads to what is called thermal stratification, that layering, and what prevents that free mixing of the water column. What ends up happening when we restrict the free mixing of the water column is that we impede the ability of all of the lake water to become naturally reoxygenated. And that normally happens as a result of water being exposed to the atmosphere. And so at this time of year, as I'll show graphically, it's very easy for the lake to mix vertically, even at its deepest points. And as a result of that water being swept back up to the surface, exposed to the atmosphere, it becomes reoxygenated. So the lake has a high amount of oxygen in the water column. However, when we end up stratifying the lake, we end up with these layers in the lake. The deeper waters of the lake, because now they cannot mix freely up to the surface any longer, become quickly depleted of oxygen. And that's because of all the bacterial processes that are occurring in the sediment, all the decomposition. There's a lot of respiration that occurs that utilizes oxygen. And as a result of that, in very short order, days, you can have zero oxygen at the bottom of the lake. And when you have zero oxygen, no measurable dissolved oxygen in the water, that condition is referred to as anoxia. So, some terminology, but this is terminology that we end up using throughout the report. So it's good to, sort of familiarize yourself with some of this. So here's a graphic that shows typically what happens with Honeoye Lake and a majority of lakes that are deeper than about 8 feet or so. In the spring, this time of year, the nights are still cool, the days are somewhat cool, surface of the water is somewhat cool, and it's about the same temperature as it is at the bottom. So temperature and density of the water column is pretty uniform. And as a result of that, wind and wave action can circulate the water column very easily. And this even happens in lakes that are like 60, 80 feet deep. In the summer, though, we have longer days. It gets, air temperatures are warmer, and very quickly the surface of the water becomes warmer. And as a result of that, it becomes less dense. And so now you end up with that layering that I referred to previously. And when there is enough resistance to that mixing, we end up with what is referred to as a thermocline. Now, we've all experienced this. You dive into the lake in the middle of the summer, it's really warm at the surface, and all of a sudden it gets cold really quick, and you've broken through the thermocline at that point. You've gone from that warm, less dense layer into that cooler, denser water. But that thermocline prevents the vertical mixing of the water column. It takes a lot of energy to break down that boundary layer. But in the fall, the days get shorter, air temperatures start to drop, and then as a result of that, the surface of the lake becomes cooler, reaches the same temperature and density as the water at the bottom, and then the lake turns over. A lot of us are familiar with that terminology, a fall turnover or an autumnal turnover. And that's really just a function of that thermocline breaking down and the water column, once again, vertically mixing. So a little bit more terminology that we need to touch on, but that epilimnion, the upper layer of the lake, where it's warm, plenty of sunlight to support photosynthesis, and it's oxygen rich. The metalimnion, or that middle transitional layer where the thermocline exists, cooler temperatures, typically measurable amounts of oxygen, and maybe not enough light for photosynthesis. The deeper portion of the lake, though referred to as the hypolimnion, is cold, remains cold throughout the summer, but it's oxygen poor. And on top of that, there's not enough light down there to support photosynthesis. But as I mentioned before, that thermocline, that boundary, really is a restrictive horizon that prevents that bottom water from mixing to the surface. And, graphically, again, we can look at this, again, a little bit of terminology, but that oxic zone where there's plenty of oxygen, think of it where there's enough oxygen to support a variety of different types of aquatic life, aerobic life, including fish. The thermocline, that middle boundary, and then the bottom of the lake, the hypolimnion, which is anoxic, no oxygen at all, or hypoxic, meaning that there might be a little bit of oxygen, but not enough to really support fish life. Okay, so the stratification impacts when a lake thermally stratifies, not only Honeoye Lake, but other lakes that thermally stratify. That sets into action a whole bunch of biological and chemical changes. And even if this only persists for a short amount of time, days, not months, but days, that can result in some significant impacts. Primarily the loss of oxygen down at the bottom, referred to as hypolimnetic anoxia, a tremendous amount of phosphorus released from the sediment, referred to as internal phosphorus recycling. That internal phosphorus recycling can stimulate algae blooms if some of that phosphorus makes it up to the surface, as well as cyanobacteria-supported harmful algae blooms. And in severe cases, it can even lead to fish kills, thermal stratification, and anoxic conditions. So aeration can be used to manage thermal stratification, can be used to mix the lake, it can be used to correct deep water anoxia, and it can be used to manage that internal phosphorus load. Okay, a little bit more terminology. Limnologists love terminology. We love to put things into little boxes and try to, put little stamps on things. But a lot of lakes, particularly deep lakes, tend to stratify and destratify 2 times a year. And those are referred to as dimictic lakes. They have very stable water columns. So there might be a little bit of turnover that happens in the spring during ice out. And there's a large amount of turnover that happens in the fall, that autumnal turnover. But dimictic lakes only turn over twice, once in the spring and once in the fall. So during the summer, the water column is very stable. Polymictic lakes, which are very common in the Northeast, they tend to stratify and destratify multiple times. So although they stratify, the thermocline is somewhat weak. It's enough to typically keep it in that thermally stratified state, but it can be upset, it can be broken down at times. So the water column tends to be much more unstable. And you'll find that there's multiple occasions during the summer where the deep water flips between an oxic, presence of oxygen, and an anoxic state, presence of no oxygen. Honeoye Lake is a polymictic lake. And a lot of the data collected by Dr. Harrison demonstrates that unequivocally and actually sets the stage for why that happens and why that thermal stratification breaks down, but sometimes multiple times during the summer months. Okay, so how can we reoxygenate the bottom of the lake? And as I mentioned, there's 2 different approaches. We can mix the water column, circulate it vertically, prevent that thermal stratification, and maintain the exposure of the entire water column, including the deep water, to the atmosphere. In doing so, then we maintain oxygen levels throughout the entire water column. Or we can oxygenate the water column and actually infuse or inject, quote unquote, pure oxygen into that deeper water. We don't alter the thermal profile of the water column. We're not mixing it, but we are introducing oxygen down at the bottom that does what we need to have, that we need to do, and that being maintain oxygen levels in the hypolimnion, thereby keeping all that phosphorus bound to iron. And that can be done without altering the thermal profile of the water column, without de-stratifying the water column. So graphically, mixing options utilize compressed air to either partially mix the water column or fully mix the water column. And then we have pure oxygen injection systems that are utilized to introduce oxygen down to the bottom of the lake, or whatever level that we would want to introduce it, but at the bottom of the lake in our case, and maintain oxygen levels without altering the thermal profile of the water body. So full lift, partial lift, full lift is what has been proposed in the past for Honeoye Lake, referred to as a destratification system. And they're very effective for deep to shallow polymictic lakes and used quite extensively throughout the nation. Partial lift systems are more designed for deep dimictic lakes. You may know some of the terminology, hypolimnetic systems or layer air systems. But really, the bottom line is that for Honeoye, being a polymictic lake, full lift destratification has been identified as a viable option. It's something that I identified as an option back in my 2007 report, and has been identified as an option in multiple reports by others, including DEC. So again, just a graphic, and I want to just emphasize here is that the compressed air is not what oxygenates the lake. It's the moving of the water column, creating almost a convection current, like boiling a pot of water and keeping that water column moving, exposing the water to the atmosphere and then allowing it to reoxygenate. The original concept that was actually discussed in detail in the report that was published by Princeton Hydro in 2020 after a review by DEC. That report was actually finished in about 2018, but went through extensive DEC review. Called for a destratification system consisting of 125 horsepower compressors. We looked at 2 locations, but at that time settled on Sandy Bottom Park, the north end, as the location because of the availability of the correct type of power. Those 2 compressors would provide compressed air to 24 diffusers But that amounted to not only 24 diffuser setups on the bottom of the lake, but also almost 300,000 feet of airline on the lake bottom. All of the land equipment could be placed in a 20 by 20 shed, and that compressor house would be fully insulated, sound deadened, etc. The estimated capital cost for that project was between 1.7 to 1.8 million. That's for the construction, installation, permitting, everything that it would take to put the system into the lake. And the estimated annual operating cost was upwards of $75,000 per year to run that. So that is presented in detail in that 2020 report, as I said, which was done for DEC and published in 2020. There's better ways to do that. And luckily, we had the ability to work with Dr. Paul Ganser and look at these pure oxygen systems. And one of the systems that proved to be particularly effective, potentially effective for Honeoye would be a side stream saturation system. And as I said, this does not require the full mixing of the water column, so that we're not disrupting the thermocline. It does, and yet what we can do is have a much more precise means to maintain deep water dissolved oxygen concentrations. We're not at the whim of water temperature or the amount of exchange that's happening with the atmosphere by moving that water up to the surface. We're actually injecting oxygen into the bottom of the lake, into our targeted zone. You'll be seeing, a couple of other, examples of the system, but just in cross section, essentially it's a pretty simple system where we have pumps that pull water out of the lake, out of the deepest portion of the lake, bring that into a pump house, mix that water with oxygen, and then that water is then returned back to the bottom of the lake. And again, this is all done without disrupting the thermocline and without creating these really immense underwater eddies. None of that occurs with this type of system. Some of you may be wondering, where does this oxygen come from? And yeah, there are certain systems that are in place around the country that actually have on-site oxygen storage, which means a tank truck needs to come every couple of weeks or so and deliver oxygen. That's not what we're going to be doing. Our system is designed for on-site oxygen production, and this uses technology very similar to what is used in hospitals around the country to actually produce oxygen. So there's no need for these large outdoor storage tanks, and even the inside, the equipment that is interior to the building is relatively small. So on-site oxygen generation, and Dr. Ganser is here, and he'll be able to answer some of these questions better than I can. But essentially, the guts of the system is a pressure swing absorption unit. And what that does is strips nitrogen from compressed atmospheric air. So we're pulling air from the atmosphere. It's being compressed, and then we're stripping nitrogen from that atmospheric air. The nitrogen being the most prevalent element in the atmosphere. And then by doing that, we can maximize the amount of oxygen that is present in that compressed air. So there's no need to store this in very large tanks. The tanks that the air receiver that is used to store the compressed air is about the size of what you would see with a typical destratification system or any other type of aeration system. So you don't have to have any tank trucks delivering oxygen to the site. It's not like we have large, cylinders of oxygen inside of the building, et cetera. And like I said, this is the same type of technology that's used at hospitals around the country. We'll come back to this, and I've got some different graphics that show this a little bit better, but this is, for comparison to the D-Strat system, we're only in need of one 20 horsepower compressor as opposed to two 124 horsepower compressors. That air set model pressure swing absorption unit, as I said, that is like sort of the heart of the system. We have 2 water pumps, each one at about 15 horsepower. There is some parallel water intake lines, parallel water intake and discharge manifolds, and everything is stored in a building on the land components, in a 20 by 20 to 20 by 30 fully insulated, sound deadened, and vented pump house. The estimated capital cost with this system is 1.2 million, so significantly less than the D-Strat system. And the key thing here is that the annual operating cost is between about $35,000 and $50,000 per year. So again, significantly less than that associated with the D-Strat system. So how is this saturated system better than D-Strat aeration? Well, number one, as I mentioned before, and I'll reemphasize this, we don't disrupt the thermal properties of the lake. Number one, we're not relying on the atmosphere to do the reoxygenation. So we have much better control of the amount of oxygen that's at the bottom of the lake. We direct the oxygen to that portion of the lake that needs it the most, and that is the hypolimnion. So we can direct it to the deep water portions of the lake and maintain it in a oxic state. And then it's much more reliable means than destratification or hypolimnetic aeration of creating and maintaining deep water fish habitat. So this is the schematic again. As I mentioned, Dr. Ganser is with us tonight. He can talk about the various elements, but this is similar to what I showed you pictorially a couple of slides back. Intake manifold, intake lines, brings the water into the pump house. The water is then mixed with oxygen and then returned to the bottom of the lake via discharge lines in a return manifold. We'll zoom in on this, momentarily, but for this project, because of some factors that were not available to us when we're looking at D-Strat, we use a conceptual pump house location at California Ranch Point. Our targeted zone is that deep blue portion that is on this slide and represents water that's about 25 feet or deeper. All right, so the components here again, there are 2 parallel water intakes, each about 750 feet long. Those draw in water at a very nominal rate. That water is then pumped into the pump house via 2 parallel intake lines, each about 2,300 feet long. The water is mixed with oxygen and then returned again via these 2 parallel discharge lines, again about 2,300 feet long, and then discharged at a nominal rate at the bottom of the lake via 2 discharge manifolds, each about 750 feet long. So zooming in a little bit more closely, what I just want to emphasize here is in the bottom left-hand corner, is that all of the in-lake elements, the manifolds, the intake line, the discharge line, those are all firmly anchored to the lake bottom. And Dr. Ganser has done a number of these installations. But what is unique about this system is that it also includes a buoy line. That buoy line can be pumped with air, and that will actually lift the system up off the bottom for ease of inspection and servicing. And so even with 2,300 feet of line, we can keep that line down at the bottom, close to the bottom, but at the same time, when we need to raise it for servicing or inspection, it can be easily raised. These lines are extremely durable. Hooking them is going to be no problem. Even anchoring, if an anchor gets stuck on them, again, that's not going to be a problem. The anchor line will probably break before the air line does. And there's other aspects about this design that make them almost like a series of segments, so that if one element or one segment is impacted, it doesn't result in the whole system shutting down. The conceptual pump house rendering, this is just to kind of give you an idea. This is an isometric drawing, but it could be between 20 by 20 to 20 by 30, but fully insulated a low profile building, and within which there'll be everything stored. There'll be security. We'll try to screen this as best as we can using a combination of vegetation and maybe some fencing. And then within the unit, you can see basically the general layout of all of the equipment. So there's plenty of room in a 20 by 20 or 20 by 30 building for all of the equipment, easy enough to get to service, to inspect, etc. So the benefits of side stream oxygenation really is that multiple studies have shown it to be extremely effective at controlling and decreasing internal phosphorus load. That's our primary goal, okay? And compared to destratification systems, lower capital cost, and definitely lower long-term operational costs. And as I mentioned previously, for this system, estimated capital cost of about 1.2 million and annual operating costs between 35 and 50,000. The other benefits of side stream oxygenation is that, as I mentioned previously, we're not at the whim and of the water density, temperature, DO relationship. So it's not affected by any of those limitations. We're not affected by any daily changes in water or atmospheric oxygen exchange rates. The big thing is that, again, it does not alter the lake's thermal profile, and we can specifically target where that oxygen is going to, making sure that we're extremely efficient in oxygenating the bottom of the lake. And that has, the secondary benefit of increasing fish habitat at the bottom of the lake year round. I'm going to turn the presentation over to Betsy and Terry, and they'll just talk about the next steps associated with the project. So go ahead, guys, take it away. I'm going to, I'll stay on here, but go ahead.
All right, thank you, Steve. This is Terry Brownwell again. And I do want to emphasize, I forgot to emphasize it in my welcome, that you can think of this project that we're sharing with you as a feasibility project. You can think of it as trying to answer the question, is aeration a cost-effective way to reduce the frequency and severity of harmful algae blooms at Honeoye Lake? So this is not a meeting to make a decision, yay or nay, but we're sharing our findings. And thank you very much, Steve. And we will be getting feedback from all stakeholders. Those of you on the WebEx here, the town boards, Richmond and Canadice, key decision makers in the county, and most important, the New York State Department of Environmental Conservation. If the overwhelming feedback is positive, the next set of bullets just gives you a sampling of what lies ahead. We got to do a lot more work on operations and maintenance planning and sizing. We probably have to do a more detailed engineering design with engineering drawings. We have to finalize a location for the shore-based equipment, which means we have to find a lakefront property owner, preferably on the east shore near the center of the lake, that's near the deep water. And we have to secure that site. We have to secure the funding. Last year, New York State WQIP grants offered up to $1 million of grant funding for an aeration system. Have not seen the guidelines for 2022 yet, but there's a significant 25% local match. So remember, Steve and Paul's and Scott's estimate is 1.2 million. So that would be, using that literally, that would be a $900,000 grant and 300,000 of local match funding. And most important, is the impact assessment going through the secret process, permitting process, going through all that. There will be formal public hearings. We have done that before, so that is a fairly extensive process. Everything Steve presented tonight is in a draft report that is posted on the Honeoye Lake Watershed Task Force website. And you can't click on it. That's kind of a long URL there. You can either Google on Honeoye Lake Watershed Task Force and you'll get to the website, or you, at the bottom of this chart, you see the www.honeoyelakewatershed.org. That is the website. You go there, go to resources tab, and you will find the draft document that Steve has been basing his presentation on. So again, I emphasize, we're sharing this to get everyone's feedback, all key stakeholders of the lake, residents, towns, county, DEC. It's very important before we can make a decision of this is our long-term solution we want to pursue or not. Now, Betsy Landry is going to help, and we're going to move into.
Yeah. You're muted. Okay, thanks everybody. Good evening. Thanks for joining us for this presentation. Right now we have 5 questions in the Q&A, and I welcome anybody who has a question to go ahead and type it in, and we're going to refer these to our panelists. So I'll start with Mitch Cantor's question, which is how many pounds or kilograms of algae is present in the lake during a HAB?
That's a really
Steve,
good
can you
question.
address that?
Yeah, I mean, that's a really good question.
Oh, Steve is muted.
You hear me?
Ellie?
Can't seem to unmute myself here.
Yeah, you're good. We can
Steve,
hear
are
you.
you
Steve.
muted?
Okay, all right, you can hear me. Okay, fine. No, that's a really good question, and honestly, I've never quantified that. I can't tell you how many pounds of algae, because normally what we utilize is lake water clarity, and we know once we get below 3 feet of clarity, we have a bloom, and you know the severity of that bloom then increases exponentially as we go from 3 feet to 2 feet to 1 feet, and you know that at times, you know, a lot of those cyanobacteria cells, the blue-green algae, get pushed into like the north end of the lake and become these very, you know, significant slimes, you know, surface scums. The number, I don't really think it's that relevant in terms of the amount of pounds. It's really the amount of clarity that we have. And our goal is to maintain probably on the order of 3 meters, somewhere close to 9 feet or so of clarity throughout the entire summer. That would be, I think, you know, a relatively realistic goal for Honeoye Lake. There's times when you have that much clarity, like that this time of year, and in the summer you don't. But poundage isn't that much important. It's a nice sort of like takeaway to say, okay, if I've got 1,000 pounds of algae, that's about what would be supported by a pound of phosphorus. But in reality, you know, it's how that's distributed through the entire water column. And when it accumulates at the surface, that's the problem. And when it's a HAB, that means that there's, you know, greater than 20,000 cells per ml. And that's all reflected in clarity. So clarity is probably the better way to sort of wrap your head around the severity of a bloom.
Okay, thanks, Steve. I've got my volume fixed now, everybody. Next question is from Bob Gerlach, and he asks, what happens to the nitrogen that is stripped? And is there an environmental impact from that?
Steve, I can take that.
Yeah, I was going to say, Paul, why don't you take that?
So the nitrogen that's stripped is just vented to the atmosphere, and there is no environmental impact from doing that.
Okay, thanks. We'll go on. If you want to follow up on that, Bob, if you want more information on that, then let us know. Okay, the next question is, will this approach help reduce HABs in the north and south end of the lake?
Yeah, absolutely. The problems that you see in the north and the south end are actually emanating due to what's happening at the bottom of the lake, you know, starting in the center deep hole of the lake. And as I said before, you know, wind and wave action pushes those cells and makes them concentrate at either end, particularly the north end. But this is, you don't have to, and even with destratification, you don't have to uniformly mix the water column. And definitely with oxygenation, you need to put that oxygen where it's needed the most. And that, in this case, is in those waters that are deeper than 25 feet. Paul, you want to add anything to that?
No, there really isn't anything to add. I mean, what's deceiving is that when you see your algal blooms at either end of the lake, that's where the wind has pushed it. If there was no wind, you would see it kind of propagate from the center and then slowly migrate outwards. But as the wind blows in either directions, it gives a biased amount in either cove. So, but yeah, I don't really have much more to add to that. Does that help?
Yeah, I mean, that helps a lot. And I think also, Dr. Harrison's data shows that there's like this big internal wave in the lake that pushes material towards the north. And then as that internal wave hits the northern edge of the lake, this is happening under the water. So it's not like a surface wave. This is an internal wave. Then material gets pushed back towards the south. So it's almost like a conveyor belt that is running, but the majority of the problem gets pushed to the north. But regardless, as Paul mentioned, if there was no wind or wave action, you'd see everything emanating right in the center of the lake, and then slowly sort of like diffusing outwards.
I mean, technically, if there was no wind and there was no mixing, it would be trapped in the bottom.
Yeah,
and it would stay down there until it destratifies. But because of the satiation and the wind blowing across this lake, and if I understand, it's very windy, and it's polymictic state, it's bringing nutrients to the surface, and then that continued direction of the wind is basically bioaccumulating it all in one zone, giving a biased, reading of overloaded in that one spot. If you went to the opposite of the lake that same day, it wouldn't be as bad. So,
yeah, exactly. Okay. And that's a good point. The polymictic nature of the lake, that is, it like I said, there's many lakes that are polymictic, but it is a unique feature of Honeoye that actually, escalates or exacerbates some of these problems. As Paul mentioned, if the lake was very stable, you would probably not see some of these problems until, you got into September or so, when the lake started to go through its fall turnover. But polymictic lakes, this is sort of like you see these types of problems happening where you go from relatively clear water to highly, really high dense algal accumulations in a short amount of time. And it's because you've pulsed a bunch of these nutrients that are sort of like lurking at the bottom of the lake, and all of a sudden get sort of like pushed up. And you don't need to push up all of it. All you need to do is push up a little bit of it. And as I said, that internal wave that is in the lake and wind patterns, et cetera, and the weak stratification of the lake, all work together to create those conditions.
Okay, thanks. Let's go on to the next one. Another question from Bob. And I have to scroll back up to it. His question is nominal, in quotes, intake and outtake. How does that affect the flow of water? Is there any impact on swimming in the vicinity?
Yeah, Paul, why don't you take that, because I think they're asking about the velocity of water.
I get what you're asking. Okay.
Yeah.
So our velocity headers are originally designed at 0.1 foot per second velocity over it. In other words, the flow velocity off our screens is 1.2 centimeters. Because of the nature of this and its size, I sized it 10 times that. So the flow velocity is 0.01 foot per second. So there is no measurable turbulence coming into or going out of the header. Does that help answer your question? And again, it won't affect any swimming. It will not entrain silt. It doesn't entrain any sediments because the velocity gradients are so low.
Okay, thanks. Okay, how about this one? Does the thermal profile prevent the distribution of the oxygenated water to the north and south end of the lake?
Yeah,
No,
we don't really, yeah,
No.
that's, go ahead, take
So,
that one, Paul.
the oxygenated zone will go uniformly bank to bank, side to side, end to end in its range of temperature. So if everything below 25 feet is relative to the same temperature, when I'm saying relative, less than 0.2 of a degree centigrade difference, it will disperse uniformly and throughout that entire volume. Now, if there's a temperature gradient, you won't see that water, that oxygenated water, dispersing upwards through the thermocline, but it will spread across the entire basin in its zone of equal temperature.
Yeah, so, basically, as Dr. Ganser, as Paul is mentioning, yes, we target the oxygen to the portion of the lake that needs it the most. But, Terry and Dorothy, they go out almost daily during the summer to collect data. That's one of the things that we have to our advantage. There's reams and reams of data. If you look at the oxygen temperature profiles of the lake, you'll see that the lake is very well oxygenated until you get below the thermocline. And so, those shallower areas, they don't need to be reoxygenated. They're in no need. They're at saturated levels already. So, we're putting the oxygen where it's needed the most. It's a good question. And I understand what you're saying, but you got to think of, and we have all the data to, support that. But those shallower areas do not need the benefit of reoxygenation because they are already they're already saturated. They're at the highest levels that they can reach during the summer.
Okay, thanks, Steve. What is the time frame for getting this approved to installation? Is it 1 year out, 2 years, 5 years out? I think we can answer that. We know that we went through the next steps. We do have to look at the level of community support and interest in this project. We have to do fiscal planning. We have to figure out the final elements of the land-based features. We have to have more conversations with DEC and other agencies actually about permitting and apply for a grant, receive a grant, and then bid out a project. So I think you can safely say it's a good 2 years out minimum. But no time like the present to, start moving forward, right? This would be a big project for this lake and these communities. And, big projects take a little bit of time, but I think this one is doable with all this homework that's been done. Okay.
Yeah, I think you're right with the time frame. Betsy, Paul and I are working with a lake, a large, relatively for New Jersey, it's a large lake. It's 550 acres and 60 feet deep, and it's taken them about 2 years to go through the entire process. They'll be installing, a side stream system this fall. But from the point in time when we started design to when everything will go into the lake, it's been about a 2-year process.
Mhm. Okay, thanks. Would the New York State launch property, this is the boat launch, the south end, partly qualify for an area to support the southernmost manifold?
It could, and we have looked at that. The problem right now is that there is not the required 3-phase power source, and that is the big thing. So we did look at that. We looked at, potentially siting at that location, but the lack of 3-phase power essentially stops us from considering that, that area. Now, we get a property. We don't need a really large amount of property, but can find a suitably sized piece of land with 3-phase power. Then yeah, we can move everything as Terry said at the beginning to the east shore as opposed to the west end or the west shore or the north end.
Thanks. So if there's anybody out there who has an idea on that, feel free to forward that to us. Okay, so what, if any, impact will the system have on the yearly overgrowth of weeds?
This isn't a weed control system. This is an algae control system. So it's not designed to manage aquatic macrophytes. I guess some people could say, well, if you increase the clarity of the lake, that may increase the amount of weed growth, but already the lake has enough clarity to support weed growth to relatively, deep, like 8 feet, 9 feet deep. I don't see this. I mean, honestly, we did sort of look at this as part of the DEC report that was, done through Princeton Hydro. I don't really see this as being something that would escalate weed growth in the lake. But it definitely is not something that is going to manage weed growth. This is designed for planktonic algae and specifically cyanobacteria.
Okay, thanks. And I think the next question is, will the oxygenated water help reduce milfoil growth? And I think you've answered that. No.
No, it won't. I mean, there is the premise that, oh, milfoil, the way it works, because it creates its own little micro anoxic environment, allowing phosphorus to be released, but that's local in shallow water. We are testing some prototype systems that inject oxygen, very enriched oxygen in a water directly over those sediments to see if we can mitigate milfoil. But again, it's all in theory and nothing has been applied. So it will not do anything for milfoil. Sorry.
Okay. So Jeannie Rorden asked this question. I'm going to read it. I think I understand what she's talking about here. She has friends on Juanita Lake. Now that's a small lake, kind of southeast, I believe, of Cuca Lake. It is also a very small lake. I don't have proof, but one resident thinks their lake is treated with some sort of chemical. In one of the first slides, I think I remember some sort of aluminous alum, well, basically it was alum chemical. Is there a chemical that can be used for a quicker fix if the SSS system is more than 2 years out? Well, that's a complicated question.
Yeah, it's a really complicated question because currently,
Why don't you just give an overview of elm, Steve?
yeah, I mean, so, alum is a nutrient inactivant. Essentially, it is a chemical that is utilized in the management of lakes. There is a moratorium on its use in New York. However, it is utilized to bind with phosphates, which, as you remember at the beginning of the presentation, that is a type of phosphorus that's immediately available for bioassimilation. So, alum treatments have been used historically going back to the 1980s, very effectively and very safely to control nutrients. And, if you look at some of the studies for Honeoye, there's always been the discussion of utilizing a combination of aeration and alum as a means of minimizing the amount of phosphorus that's in the water column. Right now, we don't have that option. The lake was treated with alum back in 2009, 2008, 2009. Correct me if I'm wrong, Terry. That took
in 2007.
2007. That took a lot of permitting to get that in place, and there were a lot of restrictions in terms of the amount of alum that was allowed to be used. But bottom line, if somebody's done an alum treatment in New York, unless it was overseen and by DEC, then it's probably illegal. There were a couple that were done in the Hudson River Valley a couple of years ago, but that was under DEC's direct supervision for experimentation purposes. But there are other nutrient inactivants, Phoslock, which DEC has become a little bit less restricted on, but that still needs an extensive amount of permitting. So I think I know what you're talking about, but if something like that has been used in that water body, it may have been introduced illegally. I hate to say it, but.
Okay, thanks, Steve.
If I recall, an alum dose for Honeoye is going to double your project cost.
Yeah.
I mean, you're looking at 7 figures to dose alum to that lake appropriately. So.
Yeah, to get up to where we really need it, which, the dose rates that I had kind of come up with that DEC tamped down significantly, was up around like 300, 350 gallons per acre. But yeah, it would be a significant project.
Yeah. So, okay.
And, both
Okay.
Paul and I and Scott, we've done a lot of alum treatments in New York. I mean, in New Jersey and in Pennsylvania. So, we know our way around alum and the cost of alum and the upside and the downside, but it's definitely much more of a shorter term type of fix the way it's normally used. Okay. Aeration gives you a longer term, more controlled uh, way of managing that internal load because you're constantly managing it. With alum, you dose it, you walk away, you have to come back in 5-7 years, repeat that process because you're still getting that influx of phosphorus. That doesn't make a difference with aeration. As long as you can keep that phosphorus bound to the sediment and maintain those oxygenated levels down at the bottom of the lake, you can deal with that constant influx. That over time, that's why alum treatments typically have to be repeated, or they're used in combination, like Scott and I have done, and Paul has done with others, in combination with aeration.
Okay, thanks, Steve. Will the system affect winter ice formation?
No, it's shut off during the winter.
And even if it did operate, again, it has such a low flow rate that it doesn't mix the water column. This system originally was designed for a project up in Minnesota that was 3 feet deep. And we wanted to ensure that we could prevent fish kills in 3 feet of water that had 18 inches of ice. So again, this is why our flow velocities off the headers ends in 1.5 centimeters. So there isn't any internal mixing. So it could be operated in the winter if need be, but right now it's slated to be turned off. So either way, it would not affect ice.
Okay, next question is, unfortunately, we need to worry about someone damaging the setup if they disagree with this approach. How robust is this setup to vandalism? I mean, could you comment in general about the in-lake equipment as well as what could be on shore?
Sure. So
Yeah, let Paul handle it.
Yeah.
He's got a number of these in around
Yeah.
the country
So-
for years.
the equipment on shore, again, that's whatever protections are necessary in place for the building. All pipes would be trenched to the water edge, and then what's in the water is submerged. And we're working with HDPE pipe. Unless they go after it with a chainsaw, they're not going to damage it. They're, and if it's still of concern, we can put, the first 100 or however many feet until we get down to a certain depth inside a sleeve pipe, which prevents them from even being able to access the pipes that are going in and out of the lake. So, I mean, the problems that we've dealt with in the past weren't vandalism. We had to deal with beavers. Beavers would chew through our lines and destroy our pipe because they thought it was a log at the water edge. So we ended up having to do things to mitigate the natural vandalism that we couldn't deal with. We couldn't catch them. So, I mean, let me know if that answers your question.
Paul,
get
why don't you talk about like the the line, its resiliency to anchor damage. I mean, I know fish
yeah.
books, forget it.
So
I mean, that's no big deal.
To put this line in perspective, we did a job up in Wallenpaupack, up in Pennsylvania. And the reason why we were called in, because this was a diffuser system. It had some porous hose, and they had some boiling where some porous hose had been broken. We were on site. We brought the diffuser to the surface, which is the same multi-pipe system like this. And there was this blue rope that was about 50 feet in front of us. So we drove up to the blue rope, and sure enough, a brand new Danforth anchor became part of our arsenal because it got stuck and they couldn't pull it up. When you're looking at these systems, you're looking at a 120-pound concrete anchor every 15 feet. So there's several thousand pounds of concrete that hold these lines on the bottom. And the lines themselves, as much as they'll float, if there's no anchor on them, you can't break them. I mean, we have sunk systems and anchored them wrong, and we've bent pipe in half, but still, we can't break it. So, I mean, the vandalism, like I said, is going to be from, I'd be more concerned of a beaver chewing through it than somebody trying to actually cut through the pipe. It's pretty durable. So, does that help? Steve,
Yes,
is there
it
anything you
does.
want to add to that?
Yeah, I think, Paul, the other thing you should talk about a little bit as well is the buoyancy system on it. That, and even though it's like weighted down so much, how, you know, how the system can be raised relatively easy. I mean, you and your wife just did that at
We,
at, you know,
we
at a
did.
reservoir.
So we just did a saturation system in Southern Oregon. And we put it down and, well, we got too close to our diffuser line and it took the end of our diffuser line down. So the client was on site. I'm like, okay, training session. You guys want to see how to bring these up? So we connected up our buoyancy line. We opened the valve, and within 90 seconds, the entire system was floating on the surface. We repositioned, and then we put our pump back on, and we sunk the system back down to the bottom. So, you know, other than holding the lines in place, they're actually very, very easy to raise. So we put safeguards in place so somebody can't go into the building and go, oh, what's this valve do? So we make it like double, it requires like 2 or 3 steps to be able to line up the buoyancy line, connect the buoyancy line, and raise the buoyancy line, because it is that easy to bring the entire thing to the surface. So,
Okay.
and like I said, you know, Steve was correct. My wife and I, our crew went home, we had to make a fix, and it was just the 2 of us working to fix this project. So it can be
Okay.
done. And it's very easy to do.
Thanks. So it's 8:11 and we had the session we planned runs till 8:30. I want to invite people to stay and we'll continue to address questions. I know I see we still have 74 participants. That's great. I'm going to continue to read questions that we have and we'll try to get through as many of these as we can. Any question that we don't get to, we're actually going to have our consultant team address, and in fact, we're going to be addressing all the questions. We may group them by theme because there are some repeat themes in here or repeat questions, and we will be providing written answers to those as part of our an appendage to the report. Okay. And I invite you to read the draft report because some of these questions are actually answered in the draft report. One question is about escalation of price though. But if it takes 2 years to get this done, won't the price be higher? Yes, maybe.
There is the possibility that, yes, that is true. I mean, look at what happened in prices over the last year. I mean, from when we started before COVID and then after COVID, even our small systems have gone up a significant amount. So yes, inflation is something to take into consideration.
Yes, and I'll just note that the budget that's in the report, the 1.2 million, does include a 10% escalation for the equipment, for the hardware. So we did assume that there would be some inflation by the time this project, you know, by the time we went to purchase equipment. But whether or not that's enough of an escalator, I'm not sure. But thank you, good question. All right, so since the oxygen is essentially trapping phosphorus in the sediment or keeping it bound there, if the system is ever shut down for some reason, will that drastically create an issue? So,
Not immediately.
Yeah.
So what we do with systems like this is we usually program them to operate to maintain a threshold of oxygen levels. Currently, we're doing 2 automated systems for prototypes, one in Cape Cod and one in California. And those ones are engineered to cycle the oxygen system on and off between 15 and 20 milligrams per liter. And the reason why we chose 15 and 20 is because if it were to go down, there's enough oxygen present at 15 milligrams per liter to sustain me for 1 to 2 weeks before I'm even below or even approaching 5 or 6 milligrams per liter. So, you know, part of the reason why we do systems like this is because it does give us a buffer. Things aren't going to crash overnight. Now, if you're going to fight me and says, oh, well, 5 milligrams per liter is good. Well, you have about 24 hours to fix your system before you have a problem. So, but yes, downtime is an issue. However, like I said, we engineer them to give us some buffer. And usually with mechanical things, if we can't get them fixed in a week, then I need to get myself on site and figure out why it can't be fixed.
thanks.
And I think that's a really good point as well, Paul, because, you know, the thing that you got to keep in mind, you know, with if the system goes down, as Paul's mentioning, it's not going to be on it, you know, it's not all of a sudden it's going to happen immediately that we'll be in, you know, we'll have a problem. The sizing of the system is going to be based on some additional what's called sediment oxygen demand testing. And that'll tell us what that oxygen demand is of Honeoye's sediments. And then Paul can do his calculations to then figure out, as he's mentioning, what is the correct, let's call it dose rate, for this lake. And so it's not like a uniform dose rate. And that's why this is so much better than DSTRAT, because you're not at that whim. There's only so much oxygen that water can hold, when you're relying just on natural reoxygenation. This, we can actually design it to be more specific to the actual demand of those lake sediments.
Right. So something else that's, it's kind of pseudo integrated into this project. You notice that it's called out 2 pumps. There's 2 intakes and there's 2 discharges. So you might ask, well, why aren't there 2 oxygen generators and there's 2 compressors? Well, there could be. So, and the reason why we could split that and have 2 parallel lines is for redundancy. If one system goes down, the other one will limp it along for a month. So rather than have a 2-week window, you might have a 30 to 45 day window. So, and that's something to consider. So we could very easily go to completely separate independent chains, which will increase our redundancy and increase the ability to handle a shutdown of one system or the other. And if it turns out it only needs one, then we cycle them on and off so we minimize wear and tear on one chain in itself. Yeah. And then we have the redundancy for system overage.
Right.
Okay, quick question
next.
here. What is the operating schedule? When will we turn the system on and off?
So right now in the report, we're basically showing in general, based on the data, specific Honeoye data, in terms of when stratification starts and when we normally see it terminate. It would likely be turned on in May and shut down end of September. So that can be played around with a little bit more. We could truncate that, extend it a little bit later into the season, but normally these problems manifest June, July, and August. So we have the system up and running prior to and then following when the lake typically is in that stratified state.
Okay, thanks. And what is the lifespan of the equipment once it's installed?
Okay, so the piping, it's rated for 50 years, but it normally lasts about 100. So there's no problem with any of the piping. Any of the piping in the lake, there's no moving parts. The compressor has a regular maintenance schedule, and that will run you probably 20 years. Same with the pumps. We use industrial size pumps that if you do the regular scheduled maintenance, they'll easily run you 20 to 25 years. The oxygen generator, if you continue to supply it with clean, dry air, it will run forever. Again, there is a maintenance schedule on its filters and its valves, but those are regular scheduled maintenance based on hours of operation. And if you treat it right, it will last you a lifetime.
Thank you.
And Scott can weigh in on that as well. I mean, Scott, you've seen some of these big compressors, 15, 20 years with it, if they're maintained correctly, right?
Yeah, as long as you have the proper operation and maintenance manual in place, you have trained staff and everyone is, working together to, get on schedule and maintain these systems. Yeah, they can last, very long time. It's just getting everybody, trained and having a schedule, then everything will go good from there.
That's where that 25 to 50,000. I mean, it covers all of those types of costs. It also includes, that also included costs associated with security. There'll be, a wireless security system, things along those lines that, a lot of times you don't think about in terms of maintenance, but, system maintenance covers inspection as well. And so in any event, this is not equipment that breaks down after a couple of years.
Okay, thanks, Steve. Back to biology and lake dynamics. If we increase oxygen at the bottom of the lake, won't that increase zebra mussels? Zebra mussels prefer to filter algae other than microcystis, which might then increase.
Yeah, I mean, that's something that, that was discussed with Dr. Gilman and Dr. Harrison, and, particularly Dr. Gilman. I mean, Bruce has done a lot of diving. And so, yes, is there a potential for that? Well, first off, you got to remember that what we're focusing on is waters that are deeper than 25 feet. There's not enough light down there right now to support photosynthesis. And yes, then, Bruce has seen some, zebra mussels at depth. But, I'm not going to dismiss that. But we don't see that as a major problem. And we'll know the first year we do have a little bit more involved with inspection, specifically for zebra mussel fouling of the system. But right now, I know from my experience in dealing with Dr. Gilman, there's not a lot of really good substrate in Honeoye for zebra mussel to start off with. But I think that's a fair question. It's something that will definitely be looked at in more detail when we go through the secret process. But it's not something that we haven't thought of already, and it's not something that we didn't talk about with, specifically with Dr. Gilman.
Okay, thanks. There's a question by Paul Leary, and I'm going to paraphrase just in the interest of time, and he's asking about the external load. So this solution or strategy addresses the internal load, but he's asking about what about the external load? And I think the answer to that I can shift to the Honeoye Lake Watershed Task Force, Terry. I don't think we will ignore the external load.
Well, we're always looking for opportunities to reduce the external load. That's going to go on forever. It's a journey. But there's been a number of studies over the last 20 years that have indicated in the July, August, September timeframe, and Steve can speak to this, that the internal load from the bottom sediments of phosphorus is far away exceeds the external load during that time period that we have harmful algae blooms. But we'll always have to address the external load. But in terms of the blue-green algae season, we have lots of studies, and Dorothy and I have lots of empirical data that indicate that we get blooms almost always after an internal mixing event that brings up the phosphorus from the bottom sediments. Steve?
Yeah, I mean that you're absolutely right. I mean, if you look at reports that that I authored over the years, we're not going to forget about the external load. But remember, at the beginning of this presentation, I mentioned there's three key things that make it important to deal with this internal load. It's the magnitude, okay, the total amount, and that far exceeds what's coming in from the watershed. Number two, it's the type of phosphorus, and we're dealing with bioavailable phosphorus, phosphates, dissolved inorganic phosphorus, soluble reactive phosphorus. The majority of phosphorus that comes in with stormwater is initially primarily particulate phosphorus. That settles down into the lake, and then over time it gets broken down and produces those phosphates and dissolved inorganic phosphorus that we need to fight with the aeration system. So the magnitude, the type, and then the timing. And the majority of our external load is during the spring. And at that point in time, water temperatures and the amount of flushing, although the lake does not flush uniformly over the year, during the year, but there's more flushing that occurs in the spring months because there's more loading to it. So it's a function of timing, the type, and the magnitude. And because of those, you don't want to forget about external, but that's why internal gets put up at the top of the list. It's because of those three things: the amount, the type, and the timing.
Okay, thanks. Will the project affect the number of fish in the lake?
I mean, it potentially could. I mean, we may produce more deep water, cold, fish habitat, which, could provide refuge, during the
Are you saying
summer.
affect is a negative term or affect as a benefit?
That's a benefit.
So it will be a benefit to fish because there will be a better sustained oxygen level for fish habitat. So, and again, one of the other reasons why we wanted to focus on, this type of a strategy is because we can provide you that 6 to 8 milligrams per liter, which is a better threshold for aquatic life than the 5 that is a maximum that could be achieved from an aeration system. So,
Okay, so
yes.
that's perfect because somebody else just asked, what oxygen level do you need to reach at the bottom to be effective? How hard will it be to reach this level?
I would target 100% saturation at temperature. In fact, I would prefer to be at 15 to 20, like I've talked about before. However, if we can target 80 to 100% of saturation at temperature, I'll be ecstatic.
Right. And that
Okay.
typically at those temperatures, Paul, what are we talking about? 8 milligrams per
Oh,
liter?
yeah, 8 to 10, easily 8 to 10. And how easy is it to maintain? Well, if I size my system right, no problem.
Right. And Terry, what do you see? You know, I mean, you and Dorothy collect a lot of data. When you get down around the metalimnion, what are your dissolved oxygen concentrations sort of like in the middle of the summer as you get down in depth?
You mean in the deep water, like at 8 meters?
Yeah.
Well, we typically see 0.5 milligrams per liter in there. And we see that basically nil dissolved oxygen all the way up to, oh, let's say 7.5 meters typically, 7.5 meters to the bottom.
And
So
from that point, it jumps up to what, like about like 6.5, 7, 8 in the summer until you get to the surface.
we have seen it that low. We have seen it at anoxic at 0.5 milligrams per liter, as high as 5 or 6 meters. It doesn't stay that way very long.
Yeah.
Usually we have enough mixing that it doesn't stay that way, but more than a few days.
Right.
But
So I
every
think that,
summer
you
we
know,
will see it that high briefly. But
right.
typically we see a thermocline around 7.5 meters in there someplace.
So I guess to
Seven-
answer that question, Betsy, as Paul pointed out, I mean, we'll be at least at saturation at temperature. So,
Yep.
you know, and that's a good thing.
Oh, yeah. And again, the better we can get our oxygen levels up in the bulk water, the greater we can penetrate that oxygen deeper in the sediment, the better phosphorus binding deeper down we can go. So,
And that's a good point. That might be something that definitely is worth touching on, Betsy, at this point, because, you know, the sediment oxygen demand is not just right at the surface of the sediment. There's a whole bunch of organic material that, you know, anybody that's stepped in the bottom of the lake, you know how like fluffy it is, especially as you get deeper into the lake. Well, that is creating an oxygen demand. And as Paul mentioned, you know, you can, the system can be designed to actually increase the amount of oxygen that is below right at that sediment water interface, increase, and then that decreases over time the amount of oxygen demand, and that lessens the release of phosphorus from those sediments even below the surface of the sediment layer.
so
Okay.
All right.
So it is 8:27. We have just a couple of minutes left, and I'm going to try to get through a couple more questions. Again, I invite people to write your questions in, and we'll make sure that we get back to you if we're not able to take care of them during this meeting. And we understand if you have to drop out because of other things in life going on, but we'll stay here for a few more minutes. What would be the requirements of the residents on the east side of the lake closest to the discharge and intake pipes?
Nothing.
nothing. I mean,
Okay.
there's no requirements.
And how would their life be affected on the lake? Would they notice this equipment?
Wouldn't even know it's there.
No.
And how close to the shoreline would those manifolds be?
Are you referring to the pipes that would go down to the lake or the
Yeah,
headers that are sit on the bottom?
Yeah,
Yeah,
the
They're
pipes
sitting on the bottom in the deepest part of the lake. They
Yeah, so
won't see
that's a
them.
little bit offshore.
Yeah, unless they put on their scuba gear and go looking for them.
Okay.
No, but no, they won't see that. They won't even know they're there.
Terry,
Okay.
would you estimate that we'd be at least 100 feet off the edge of the east shore?
I would say that they would be 500 to 700 feet west of the shore.
Yeah. Yeah.
Yeah, it won't affect people. They won't. And you know, again, we have systems like this running. People don't even know they're in. They don't even know they're in the lake.
Last question. Have representatives from Honeoye been to lakes where this system has been installed and spoken to local community members there?
Not a super saturated side stream system. Dorothy and I have visited a aeration de-strat system at Lake Carvey in Vermont. And it has been very effective in meeting the objectives.
And I can add to that, Betsy, because, the Culver Lake people, it's a side stream system that's going into that lake. And even with COVID, what we did provide was opportunity for them to have Zoom meetings with some of the facilities where, the system had been installed. So, there's ways to do that without actually having to traipse out, to go look at a system.
And Steve, remind people, where's Culver Lake?
Culver Lake is in northwest New Jersey. It's just about, maybe about 20 miles from the New York border.
Right.
So it's up in Sussex County.
So that's a great idea for part of our next steps is to, maybe visit a Culver Lake community, either virtually or in person while we deliberate this project.
A nice 3-hour drive, and it's in a beautiful part of New Jersey.
Okay. Props to New Jersey. Okay. I think I got through most of the questions. There might be some a little bit buried. I see that. Let me just ask you this. I don't believe I framed Paul's O'Leary's question properly on the external load. What he's saying is, will the system work just as effectively on the internal load, given that there is an external load? That was really my question. Will it work regardless of what the external
Yeah,
load is
absolutely.
doing?
Yeah.
That's a
Yes.
good question,
Absolutely.
actually.
Yes.
And most lakes that do have aeration, they're doing, parallel work with their external load as well, whether it's septic or it's stormwater or whatever. Those aren't neglected. But yeah, it to answer his question directly, yeah.
Okay. All right, thanks. I want to thank the panelists. It's been our pleasure to work with all of you. I want to thank the folks that have joined the meeting tonight and our town board members that have supported this project and the local committee. I want to thank Alex Apolito for hosting this for us. Esposito, I'm sorry. I've got the Apolitos online here. Esposito from FLCC for hosting us and being our tech guru tonight. And we look forward to working with all of you and with DEC in the future to bring this this part of the project to the end. So
Yeah, and Betsy, if I may, thanks to you and Terry, for all the support, and for all the great questions and hard
yeah,
work
great
to
questions.
get this done. And then also, obviously to Paul and Scott, because they have the technical know-how. They've been in the trenches. They've done this work. Paul is the brains behind everything. He's the he's the one who's come up and designed these systems. So we have a great team. We really do have a great team, and I think that that'll be beneficial to the Honeoye Lake community.
And I thank you for sharing, all of you for getting online tonight and sharing your faces and your expertise with us. I think it really helps the community in this virtual. We're still going virtual, but it was really great for everybody to get to meet you tonight over WebEx. So thanks.
All right, fantastic. Thank you.
All right, thanks a
Yeah.
lot.
Okay, Terry, we're going to post this presentation, Terry, on.
Yes, in a few days, I'm going to post it on the Honeoye Lake Watershed Task Force. Ali Esposito has recorded the WebEx, so we'll be posting a recording of that, and I will make it available, and it will be on the Canadicetown website, on the Richmond Facebook page, on the Watershed Task Force blog, and the HVA will send out an email announcement. So it'll get out there. So give us a few days to a week and we will post the slides and we will post the recording. And I just want to thank everybody, Steve, Paul, Scott, Allie, Betsy, Dorothy, all of you who participated and asked great questions, and we'll keep you posted. Thanks for your caring.
Thank you, everybody. Good
Thank you all
night.
for your
Have a
time.
great
Okay.
night.
Good night.
Yeah, bye-bye. So I was gonna just